Okay, hello. It's time to start our meeting. So, my name is Stratis Karadanelis. I will be the moderator of today's session. We're really keen to have two distinguished invited speakers. The first one is going to be our senior one, Professor Kingdom Abam from Nigeria, and our GEG representative, Professor Yifei from China territory. I'm really happy that we're able to provide you the third series of the e-YEG seminar, and I will move on to a short presentation of our first presenter. So, Professor Abam, Kingdom Simeon Abam, is a professor of engineering geology. He's currently vice president for Africa region of the IEG and former president of the Nigerian Association of Engineering Geology and the Environment. He holds a bachelor degree in geology from the University of Ibadan, a master's degree from Imperial College in London, and a PhD degree in engineering geology from the University in Nigeria and Nsukka. He was Director Institute of Geoscience and Space Technology at the River State University, Port Harcourt in Nigeria. Currently, he is the Director in River State University Center for Advancements and Linkages, and his research and practice are focusing on soil characterization, marine geotechnics, environmental geophysics, and coastal hazards. He has published over 80 technical articles in reputable learned journals across the globe. So I'm happy to welcome you, Professor Abam. The space is yours. Please share your presentation and you're capable of starting.
Thank you. Can you please enable the full screen? Okay. Okay. Slideshow. So, that's not slideshow. Slideshow. Great.
Okay.
Good afternoon, Stratis. First, I'd like to thank you for inviting me to make this presentation. I'd also like to extend my warm greetings to my colleague, Professor Q, who is also going to share the stage with me to discuss risk mitigation on soil. Now, risk mitigation is essentially it's about how to minimize damage, so to say, in the event of an error. And that's about you minimize the risk by fully understanding the behavior of soil. And that's why I've chosen the topic soil characterization with cone penetrometer. I'll be spending more time on data acquisition and interpretation. And I'm making this presentation from Nigeria, from this part of the world, if you look at the screen. Now, what do we understand by characterization? What do you understand by to characterize a soil? Essentially, to characterize a soil means that you need to determine the various attributes of soil. And this includes the nature, the stratification, the texture, the structure, consistency, strength, density, and several other properties. As practicing engineering geologists, we are required from time to time to provide data for making decisions on foundations, particularly for structures such as roads, for bridges, for dams, for transmission lines, and so on. So this presentation focuses on how to do all of this, and perhaps more, using the cone penetrometer, for which I have proposed the acronym CPT. Now, the cone penetrometer itself has evolved over time. The initial cone penetrometer was developed or was invented by the Dutch many years ago. And it began with a 2.5 ton penetrometer. The tonnage represents the capacity the pushing capacity. The 2.5 ton evolved to 5 tons, to 20 tons, and today we have 40 tons. These tonnages reflect the push capacity as well as the uplift resistance. Now, the initial cones that were first developed could only read the tip resistance, but the subsequent ones, with evolution with time, better cones with better resolution, with more flexibility in the probe and the parameters that are measured came on board. And so we're able to move on to be able to register the cone tip as well as the slip friction, and then subsequently the pore pressure was added. And presently, there are cones that could read up to 7 or 8 different parameters. The cone penetrometer and its advanced forms, such as the piezo cone and the seismic cone, have extensive applications, very wide-ranging applications. However, the applications are limited primarily to subsoil. But with increasing pushing capacity, they are now able to probe into stiff or very stiff soils and even to soft rocks. Now, the picture on the screen by the left is the original Gouda 2.5 ton capacity. It's very portable. You could see it could be carried by 1 or even 2, perhaps by 2 persons. It's dismantleable. It's affordable in terms of cost. These are major advantages in areas where you have very low infrastructure penetration, such as the deltas with primary forest, without roads, breaking through and all that, but you still have to get the equipment to your test point. So this was considered very convenient, but with time, penetrometers have evolved to the 10 ton. This is the Joe Mill model of 10 ton. And by the side here, you could see the 5 ton by the side of it. This is a power pack. And this is an example of the 20 ton. The 20 ton, you could see that is robust and with an electric CPT accessory. Now, the cone itself this is a schematic of a typical cone. It consists of a cone whose cone area is 10 centimeters square, as a cone tip whose angle is about 60 degrees. In Russia, they have cones whose cone angle is 90, and I think that it differs. It depends on the manufacturer's own specification. And here you have the sleeve. You'll see that the sleeve, when in contact with soil, registers the sleeve friction. You also have various probes, such as pore pressure cells. Several other cells are implanted on the sleeve. So as the cone penetrates the soil, it registers the resistances or the parameters whose probes have been implanted on it. Cones, the older cones do not have any provision for sampling. And that's one of the major setbacks of cones. They're not able to recover soil samples. But there have been advances which enable you to recover limited soil samples, as you can see from the spec on the right. Now, this is an assemblage of the cones, beginning from the single cone to the double cone. Yeah, the mechanical, both being mechanical, and then evolving to electrical cone, and then to the seismic cone. The single cone is only able to register the cone tip. And you can see that the cone does not have a sleeve. The double cone has a sleeve associated with it. So you can register the tip resistance as well as the sleeve resistance. These two are mechanical cones. They do not have accessories for pore pressure measurement. However, the electric CPT here, the electric cone here, has an accessory through which you can collect a cable that links it to a data logger and then eventually to a computer system where the digital signals of the cone resistance, sleeve friction, as well as pore pressure, and the several other probes that may be attached to it can be registered. You can see that this is a typical 35.7 mm diameter cone, whereas this is slightly bigger, it's about 50 mm cone. I will discuss the implications of size when it comes to preforming holes in the event that you meet a very stiff material, you preform in order to reduce friction to achieve greater depth of penetration. This is the example of the seismic cone. With this cone, you're able to receive seismic signals, which help you to determine shear wave velocity and eventually to shear modulus and then to dynamic modulus. Now, many of us are familiar with cones, and we're also familiar with the advantages. Using cone penetrometers, the cone itself is this procedure is a very fast procedure. You are able to obtain very, continuous profiling, and that helps you to detect thin depths and laminations, which can easily escape a driller's log. If you're drilling, for example, with flush boring, you find that many thin laminations, if a bed is less than half a meter, if the thickness of the layer is less than half a meter, it's very difficult to capture it when you're doing other forms of boring. But with the CPT, you're able to capture very small laminations as long as they are within the interval of data capture. The CPT it's repeatable. The results that you get from CPT are very repeatable. They are very reliable. They are economical and productive. And they also have very strong theoretical background. So much work has been done on the CPT. So there's a very strong disadvantage, as you could see here. Just go back very quickly. Yeah, one of the major disadvantages is that the cost of initial investment is very high. Today's price, you could spend about $25,000 as an initial, as a purchase price for the CPT. It also requires a very skilled operator. As I said earlier, no such samples are recovered, but now you have the ability to recover a few samples. Penetration can also be frustrated when you have gravelly and very steep beds. Now, let me quickly go on to the test procedure. The cone penetrometer consists of the cone, the friction sleeve, and the sensor, and the data acquisition system, which I have shown graphically. Okay, it is pushed down at a constant rate of 2 centimeters per second. The resistance of the soil at the tip, at the sleeve, and soil and pore pressure are recorded. Those are the major traits. Every electric CPT or piezo cone is able to register these 3 parameters. These are the primary parameters from which all other parameters are derived. Today, we have several other sensors which can be fitted into a cone. You can have a thermometer fitted into a cone to register your geothermal properties, temperature. You can have geophones or seismometers fitted into it to register arrival time of waves and all of that. I'll show further examples as to how that can be used and interpreted. You can also have pressure meters. You can have cameras which rely on visible light to be able to capture the state of things. You can have resistivity, pH, oxygen, redox potential, and several others. Now, the requirements for reliable tests. First is that you must have a well-trained operator. There is no alternative to this. You must also have backup facilities, and you must also have a proper maintenance profile. Now, you'll find that when a CPT probe or sounding encounters a very hard layer, you meet refusal to penetration. What do? It's wasteful when CPT encounters an unpenetrable layer at a very shallow level. There are 2 options that are open to us. The first is the pre-drilling option. When you encounter a steep layer, you pre-drill, you go beyond that steep layer, and then you continue your sounding. It is possible that the thickness of the resistive layer is very shallow. And perhaps beyond the capacity of the machine. And in any case, that's the reason why you have cone penetration that can be overcome by that. Additionally, when you pre-drill, you create some kind of disequilibrium with the water pressure. And so this process requires that you fill the hole which you have pre-drilled with water in order to ensure that pore pressure, you have piezo element saturation to ensure that the pore pressure reading remains accurate. There are cases where rather than pre-drill, you will have to use a dummy cone of a slightly larger diameter, such that I showed before, to widen the hole so that you can, and that will serve effectively as a friction reducer. Okay, now depth of penetration. The CPT, today, there are many CPTs that are able to achieve 100 meters of penetration. And that is when if the soil, that is in subsoil. They could also achieve stiff material occurs at the shallow level. And you have such stiff materials when you are working in places like the beach ridge, where you have sand formations that have been compacted over millennia, continuously by continuous wave impact and all of that. You have several, you have other places where you have very stiff materials occurring at fairly shallow level. And that's where you need the friction reducer. If you're able to reduce, if you have cones of slightly larger diameter than the rod, you're able to reduce the contact area between the rod and the soil. And that also serves effectively as friction reducer to encourage deeper levels of probe. Now, there are two things that are required that can assist you in achieving the deeper levels of penetration. One is ensuring the verticality of your sounding. And you have a maximum of about 2 degrees exceedance. You have a maximum of 2 degrees. Once the alignment, when you have an alignment away from the verticality beyond 2 degrees, then it becomes very difficult. In that way, your depth, your registered depth do not correspond with the actual depth of probe. Okay, there are some CPTs that have slope sensors attached to them, such that when you have an inclination beyond 2 degrees, an alarm is sounded to alert the operator that, look, you have deviated beyond what is allowed in the sounding in practice. There are also deviations. Deviations exceeding the norm can also signal danger. Danger in the sense that the potential damage to the equipment if the CPT deviates beyond a certain, if it is solid and it deviates beyond a certain degree. Now, the rate of penetration is dependent on the pore pressure, whether you are measuring pore pressure or not, because pore pressure needs time to equilibrate for you to be able to get an accurate reading. So if you are sounding, the sounding speed is actually 2 cm per second, that is 20 millimeters per second. And if you are not measuring pore pressure, you have a wider flexibility. You can have plus minus 20 millimeters per second, plus minus 25 degrees. Okay, but if you are to measure pore pressure, you have an allowance, you have a stricter window of 10% to operate with. Now, to avoid the effect of pore pressure dissipation, sounding has to be continuous. When you pulse in sounding, pore pressure dissipation occurs, which means that the pore pressure, if you're not sounding continuously, the pore pressures that you're obtaining may have some difficulties. Now, frequency of sounding, you have to take account of the interval. If you want to capture thin layers of soil, the properties of thin layers of soil, then your interval of sounding, your interval of data capture must be smaller than the maximum thickness that you have to capture. Data acquisition using the CPT essentially has, as I have said this earlier, you have the cold tip resistance, you have the slim friction, you have pore pressure, your electric CPT, your piezo cone also captures verticality, and you also have ability to capture shower wave, conductivity, and several other probes, as long as they are implanted on the plate. The number of readings taken must be adequate, to obtain the data. Now, using the 2.5 ton, data has been presented in more like a table, which doesn't really give you much information. You have depth, you have cone tip resistance, and then you have the total cone, including the tip as well as the sleeve. This hardly conveys any information using the 10 ton, sorry, using the 2.5 ton, for example. Okay, and this presentation is about optimizing the 2.5 ton, which has been found very useful, particularly in areas of low infrastructure penetration, where you hardly have roads, and yet you have to take the equipment to the appropriate site and run the test. Now, data, how do you present data using this kind of information? Of course, you would need you plot your pore pressure versus depth. You can also plot your sleeve friction versus depth. There are graphical ways in which this can be done. Versus depth. You can also have your differential pore pressure versus depth. Now, basically, a data presentation in CPT would look something like this. You have the cone tip presented here, the cone tip given in MPa, megapascals against depth, and you have the friction ratio. The friction ratio is essentially the ratio of the sleeve friction over the tip resistance. It's a ratio multiplied by 100 to transform it to a percentage. You also have pore pressure, and here you have the soil behavior type index. The soil behavior type index just tells you that, look, the soil behaves like clay, or it behaves like silty sand. It's not categorical. There could also be ambiguity. I would explain that further. Now, you see here, when you look down here, you see that this is the SBT window, and in most SBTs, on the friction ratio. So to some degree, this axis would also reflect the CPT. Each band, each color band here represents a particular soil. And this is this line here is the profile, is the SBT profile of the soil that is encountered. As you go down, you encounter different soil layers which have been extracted here. Take, for example, at this point, the soil is within the green window. The green window is, but here you find that the soil is peeping into the brown, which reflects the different soil types. Okay. Now you can also, if you have measured the shower wave velocity, it can also be incorporated into your graphic. And this also remains your SBT, the soil behavior type soil classification, which is associated with the combination of the slip friction and the cone resistance. The methodology for the seismic cone is fairly simple. In the case of a seismic cone, you have your cone sounding here. When you have an energy source here. Here is generated with a hammer connected to the trigger. Okay, well, you see that it's from a fixed distance to the probe, to the cone. And when you sound to this level, you trigger the sound. The energy is transmitted. Because the cone here has a listening device, a seismometer. It records the arrival time. You know the distance from the source to the sound. You also know the depth. You are able to calculate this distance, and you know the arrival time, the travel time of the signal. So you are able to determine the shower wave velocity. This helps you to determine your shower modulus, and from the shower modulus, you're able to determine your dynamic modulus. Prior to the development of a seismic cone, shower modulus was determined essentially from you have to drill 2 boreholes. In one borehole, you put a source. In the other borehole, you put a listening device, and then that's the downhole seismic. So essentially, using the seismic cone, you see that it's an effective replacement alternative to the downhole seismic, which is recommended by most commercial houses. Now, the CPT itself, many parameters, the parameters that the CPT is able to determine, there are different degrees of reliability to which it's able to determine these parameters. In this table, you find that 1 shows you high degree of reliability, 2 is high to moderate, So essential strength are the two parameters that the penetrometer is able to determine the very high degree of reliability. There are several others which are high to moderate. That's the window of 2 and 3. And so a lesser degree, these ones are determined not as accurate as can be, but to a reasonably acceptable degree. There are also others for which a CPT prediction would be considered very doubtful. Okay, and the challenge for us, I'll come to the end of this. I've shown a challenge based on these observations, which I would bring to the notice of our listeners. Now, how is CPT able to predict soil properties? There are many correlations that have been proposed by researchers in the past. For example, the friction ratio, as defined earlier, is the ratio of the slip friction and the tip resistance, so that can be normalized with respect to overbody pressure. You can also determine unit weight, which is essentially by this relationship developed by Robertson, 2010. You'll find in this graph, for example, it's a relationship between slip friction and unit weight. This correlation involves 1 over 1,000 samples, and you have a coefficient of determination of about 0.6. You find that different soil types have been embedded into this. The different colors represent different soil types. That's the linear correlation here, and there is also one that is not sort of a curvilinear, so different degrees of reliability. Okay, and moving on. You would have, how are you able to identify the soil in a comb penetrometer test? And how into the picture? In 1965, Begerman evolved a way of characterizing the soils that are encountered by the comb penetrometer using essentially, can I minimize this? Using essentially the friction ratio. The reason that if the friction ratio is between 1.2% to 1.6, that soil is most likely to be coarse sand. And if the friction ratio is between 3.2 and 4.1%, that soil is with its clay or loam or loamy soil, especially. And for peat, in peat, you have friction ratios that are greater than 7%. Recall this graphic. You find that if you look at this graph here, the x-axis, I've shown this graph earlier, just for comparison sake. This axis, you see the soils in different bands, different vertical bands. But as the profile touches that, you're able to capture the particular soil type that is implicated in the sounding. Now, Schmidtmann in 1978 made an improvement over the classification of Begerman in 1965. For Begerman, for example, the sandy formations that are encountered by the sounding have now been further classified into loose, to sand, and to dense sand within the same window of a friction ratio. And the same thing applies to the other soil types. And that is why you are able to see these gradations. So much work has been done in soil classification using the comb penetrometer. Voss in 1982 also evolved a soil classification system based on the friction ratio as well. His work is a further refinement to the work done by Begerman in 1965. And you find that here, for example, for coarse sand, which Begerman zeroed between 1.6 and 1.2, he's come further to say, look, this coarse sand and gravel should actually be with friction. If the friction ratio is less than 0.5%, then they are much surer. So the classification of Voss 1982 is much stricter than that of Begerman. Now, I'll move on to the soil behavior type index. This index is thought of as a representative. When you combine the cone resistance and the friction ratio, Robertson 1990 produced some concentric circles which corresponded with the different soil types, which he now tagged the soil behavior type index, given numerically by this expression. Okay, and these are like concentric circles. Okay, I won't, because of time, I will just move a little faster. Now, using the method, here is a comparison of the methods, the soil classification using Robertson and the improvement they made in 1990 against that of 1986, and the common soil behavior types that are registered against it, just for perhaps you spend a little more time when the slides are forwarded, you'll see that. Now, Jeffries and Davis in 1993 introduced the elements of standard penetration test. That's the SPT, which has a much longer history than CPT. You have to also integrate the CPT, so the CPT with results of the SPT together with the soil behavior type index to arrive at some soil classification, which he now compares with Robertson 1986. You can see using the elements of SPT, SPT-N60, you have the different soil types identified here correspond to the soil type developed by Robertson 1986. So you can see that you can achieve further improvement by expanding the parameters used for the determination of the different soil types. The shear wave velocity can be, there are two different ways in which shear wave velocity can be determined empirically. Now, much of the predictions made by CPT are empirical based on some theoretical background. For example, Robertson 2009 gave this expression for the prediction of shear wave velocity. In this relationship, this coefficient is given by this. Many in 2006 also determined shear wave velocity using this relationship. I think the preference, some of these have some conditions under which they can be applied, depending on the environment in which the field sounding of the CPT is carried out. And shear wave velocity essentially is just, you fit in the shear wave velocity which you have determined from the CPT into a petrophysical equation. In this equation, the G0 is your shear wave, is your shear modulus, so to say. Hydraulic conductivity can be determined to a less reliable degree. Even so, for different conditions of the SBTI index, which is the soil behavior type index, less than 3.27, you can use this. But for all other conditions, in other case, if the soil behavior type index is more than 3.27, you can use this behavior. In fact, last year in Korea, there was a further development which gave much higher reliability of using the CPT to determine permeability. Okay, so the science is evolving. Changes, reliabilities of prediction are increasing with further research. The angle of internal friction can be determined in several other ways, but I've captured two ways here. The first is by Robertson and Campanella, 1983, and the second is by Kulhaway and Mail, 1990. Okay, now here you have angle of internal friction plotted against normalized cone resistance, and this is the kind of plot you have. The green line is by Uzeli 2013, while that of Kulhaway is the red line. You'll find significant fit using both methods, although there is some paucity of data points here to determine the reliability at this point. Relative density was predicted by Demiowski 2001 using this relationship. I have to move pretty fast. On drain strength, it's given by this relationship. The determination of the on-drain strength is actually based on the Terzachi's bearing capacity equation for bearing capacity. And in this relationship, the NK here is the cone factor. And it's variable depending on the soil type. For us here in the Niger Delta, the plasticity of our soil, lateritic soil, the plasticity of lateritic soil, which is predominant here, is about 14. And through long years of experience, we have determined that the cone factor applicable for the Niger Delta, for example, is between 17 and 18. Using that, in some other places, you have the cone factor of 12.5. So essentially, it's dependent on plasticity, and you can also see that from this chart. Okay. Now, we have gone further to look at how best to predict shear strength. In this relationship, you have the undrained strength plotted against the tip resistance for both mechanical and for electrical cones. And you'll see that there is significant fit. You see coefficient of correlation of 0.92. I would consider the 193 samples. Okay, and in this relationship, the slope of this graph is essentially your cone factor. And for the mechanical cones, you find that the cone factor is 18.9, whereas for electric cones, the cone factor is 17 point, which means that the electrical cones showed more sensitivity, so to say. Here we have plotted the undrained strength against, well, I didn't plot, this is somebody's work, which I must have to acknowledge properly. He's plotted the slip friction against the undrained strength for both electrical and for mechanical cones. And you find that for electrical cones, you have parity between the ratio of the slip friction and the undrained strength is 1, which means that the slip friction can in fact be used as the undrained strength, can be considered as the undrained strength. You have a slightly higher value for mechanical cones, which means that for electrical cones, and it's understandable. Now, for soil sensitivity, which is sorry, that should be faster. Okay. Now, the sensitivity here, you have the undrained. It's a ratio of the undrained strength against the slip friction, against the which is the remolded strength, more or less. And then you can also use the CPT to determine the fines content using the SPTI, using the soil behavioral type index. You're able to have an estimate of the fines in the soil. You even for young modulus, which is determined in this way. Here you have that the cone tip you subtract the overburden pressure from the cone tip multiplied by this coefficient, which is given by this, and the soil behavior index is also a parameter here, just as you have this. So the cone penetrometer parameters are increasingly coming up for many parameters. It means that because they are there, knowing their value, you can retrospectively determine those parameters. Even for California bearing ratio, CBR, which is a parameter required for road sub-base and subgrade, the CBRO is related to allowable bearing pressure, which are related to the undrained strength, which can be determined from the cone penetrometer. So using the cone penetrometer by extension, you can determine your CBRO to some degree. Additionally, you can also, from the cone penetrometer, you can determine to some degree, it may not be highly reliable, your mean particle sizes. This is the work done by Robertson et al. 1983, and you can see the degree of correlation here. It's as high as 0.82, where 337 samples were considered. And here we have also looked at using the friction ratio against the undrained strength. You'll see for 90 samples, we had a coefficient of correlation of 90, and empirical relationships have been developed therefore for friction ratio against it. So if you have your friction ratio, you can predict your particle size distribution to some degree. You can determine your mean size, not all the particle size parameters. And soil compressibility, which is essentially knowing your coefficient of volume compressibility or your compression index, you're able to determine you can determine settlement using this equation, which if you have used the compression index, the equation will transform to this essentially. And using the constraint modulus, which is the parameter determined by the CPT, the constraint modulus is just an inverse of the coefficient of volume compressibility. Okay, so if you feed it into that, so the equation which I have shown earlier, which is this equation, just by replacing this with the coefficient, with the constraint modulus, you are able to also obtain a settlement. This is the stress increment. This is the thickness of the compressible layer you are considering. Okay, so there are different methods to estimate compressibility settlements essentially. And whereas there are several methods, I've zeroed in using Spangler 1972, Just and Ross 1995, and Main 1990 as examples. And I try to compare all of them using the CPT, basically. And if you are to use the constraint modulus, the relationship between the constraint modulus and the cone penetrometer it's a very simple linear relationship. Okay, and this coefficient here depends on different soil types, and it also depends on the cone tip resistance. So if you know your cone tip resistance, you're able to select your appropriate coefficient, and you can get your constraint modulus. Yeah, the constraint modulus can also be determined using this relationship, and this is by Colaway and Main. It's also a very simple linear relationship. In this relationship, this is your overburden pressure. Okay, you can also determine your coefficient of consolidation in the horizontal direction because the cone penetrates horizontally, and you're able to determine, and this determines the weight of settlement to some degree. Now, how is all of this applied? First is the application for bearing capacity. You're all familiar with the Terzachi's basic bearing capacity equation, which gives you this. Here, the thing here is your undrained cohesion, which you can determine using the CPT by this relationship. Here, the N is the cone factor, and if you have undrained conditions, it means that your bearing capacity factor gamma here is going to be 0. So you are just considering these two parameters essentially. Yeah, using for settlement computation, you can determine your compressibility can be determined directly based on the Bayer and Martin 1957 by this relationship. The QT here is your cone tip resistance, whereas the P subscript 01 is your overburden pressure. So essentially, you can retrofit this into the equation for settlement, and then in place of the compressibility, you can substitute this, and then you integrate it across the depth of a sounding, and then in that way, you're able to obtain your settlement computation, so to say. I'll show you the example. So here too, using a Spangler 1972, you have your coefficient of volume compressibility given as this, which here, the alpha here varies between 3.6 to 6 for the typical soils that we have here in the Niger Delta. So that fits in closely into that equation. Whereas Colaway and Main 1990 give the coefficient of volume compressibility as this. I'm showing you this so that when you see the comparison, you see that the margins of error are very minimal. Just quickly. Now, if you have used the 2.5 ton penetrometer, for example, you'll recall that the 2.5 ton penetrometer does not have a pore pressure cell, so you don't measure pore pressure. However, you can assume hydrostatic pressure distribution. So the point at which groundwater table is encountered, you can assume that for us that is true because artesian conditions in the delta are very few and far between, except for much deeper horizons where you're concerned with water, where you have to build for water supply. But basically, most of our hydrostatic conditions, you can say they are standard. They follow normal hydrostatic pressure distribution. So using these parameters which I have described to you, and using the 2.5 ton, I have this case history to report where you have tip resistance, you have the slip friction, you have a friction ratio, you have the indicative soil, the soil behavior type. This is using your conditional formatting basically on Excel. These things are generated using Excel. So using the relationships which I have shown, you're able to generate a profile, of the sounding for the undrained strength. You're able to generate your allowable bearing pressure if you are designing for foundation. You're able to generate your unit weight profile with depth. You're able to generate your angle of internal friction with depth. You're able to determine your settlement distribution. Now,
This Professor Abam conclude.
Yes, I'll conclude shortly. This is very interesting because here you are able to see that so much more settlement is contributed. If you look at here, I've generated a percent 90 over 90, for example. First decisions can be taken looking at this. Here, you're able to look at the CBRO profile. You're able to look at the cumulative. Here, you know that total settlement is just about 42 mm. Okay. And then for the different methods of settlement computation, I have done a comparison to show that any of the methods can be used, but there are margins of error. And here also, I've looked at the stress distribution from a load on the surface of a ground. This will give you the stress distribution against allowable bearing pressure. And this can help you to determine the depth of embedment of your shallow foundation. For example, and for particle size distribution, these have been shown. Now, this is just a scenario where you have 1, 2, or 3-story buildings. The stress induced by these buildings are given by these lines, whereas the allowable bearing pressures are given by these other lines to different factors of safety. So this helps you also to choose, depending on the factor of safety that you want to operate with. It helps you to choose your depth of foundation. Now, lastly, I want to say that as engineering geologists, we come to the table with a superior knowledge of geomaterial to improve the reliability of CPT prediction. If you look at the table I showed earlier, you find that the CPT is predicted to less desirable levels of accuracy. And moving forward, I would request that younger generations of engineering geologists pay attention to using their superior knowledge of geomaterials to increase the reliability of CPT prediction of soil properties for these areas. Thank you very much. Yeah, thank you.
Thank you, Professor Abam. That was really interesting. That's a really nice presentation with a lot of information in that and a lot of analysis that you're providing. Let's have 1 minute to see if there are any questions and we can move on. One question that I would like to point it out is about the versatility that you mentioned. Did you try to quantify the versatility compared with the two points that you mentioned? I think it was kind of in the beginning.
Say it again.
I mean, with you mentioned once something about the versatility of the cone penetrometer.
Yes.
So did you try to quantify the difference that it makes if there is a standard deviation of 2 points?
Of standard deviation of 2 points. You mean the versatility, or you're talking about the deviation? The deviation. Are you referring to the deviation or the versatility? The deviation, you mean?
Yeah, exactly.
Yeah, there are, in fact, the allowed deviation is 2 degrees. However, the deviation is not part of the computation. It doesn't help you in doing any computation. It's only for the safety of the machine. It's only for the safety of the rod, because at higher degrees of deviation, you stand the risk of snapping. The rods might break, and you might lose your cone and several rods and damage to the system. So it's essentially to protect the system. Okay? It's to protect the cone and the system.
Okay. Thank you. So until now, we don't have any question. If any one of you would like to pose a question, you can write it down in the chat session. So for now, we can move on to the next presentation. Thank you, Professor Abam, for now. I would like to invite Professor Kui from China and have like a small presentation of him. So Professor Yifei serves as an assistant professor of engineering geology and geotechnical engineer at the State Key Laboratory of Hydroscience and Engineering in Qingdao. Dr. Kui received his master and PhD degree in geotechnical engineering from the Department of Civil and Environmental Engineering at the University of Alberta in Canada. He worked as postdoctoral fellow and research assistant professor in the Department of Civil and Environmental Engineering at the Hong Kong University of Science and Technology. His main research focused on fluid-solid coupling theory and calculation methods from granular media with application in understanding the mechanism of fine particle migration in wide-grading loose soils and subsequent mechanism of shallow landslide initiation. Welcome, Professor Kui. The space is yours, please.
Thank you so much, Professor Stratis. And I also would like to appreciate the wonderful presentation delivered by Professor Abam. So I'm very much appreciate the opportunity provided by the Young Engineering Geologist Group from the International Association for the Engineered Geology and the Environment. I think it is a really good opportunity to learn the latest development from both theory and techniques in the engineered geology in this kind of plateau. So today, I would like to mainly discuss with you on the study the mechanism of the internal erosion of the wide grading loose soil under the infiltration of rainfall. So I will mainly divide my content into 5 parts. First, I will talk about the background, and then I will just give a brief introduction on the numerical development, consider the solid and fluid coupling. And then I will talk about the pore structure characteristics of debris flow, source material in the Wenchuan earthquake area, and then followed by the microscopic process of fine particle migration in loose soil. And then I will make some conclusion and recommendations. So the 2008 7.9 Wenchuan earthquake in Sichuan, China actually triggered nearly 20,000 landslides originally. And among those, many giant landslides with volume larger than 10 to the power of 7 meter cube were found. The loosely deposited soil generated by the earthquake-triggered landslide will serve as the debris source material, and the soil will be remobilized by rainfall and transformed into the debris flow. So one typical geological hazard example is the large debris flow initiated by a heavy rainfall in Wenjia Ravine, Sichuan province in 2010. The landslide deposit after earthquake has a volume of 81.6 millimeter cube with deposition depths from 20 to 180 meters. On August 13, 2010, after several days of heavy rainfall, debris flow was initiated. During the transportation process, the debris flow entrained the loose slope deposition with the maximum depth of the channel incision of 50 meters. So here is the disaster chain, and we can see that other 20 debris flow appeared in the Qingping town at the same time, which resulted in 12 fatalities, 300 houses destroyed, 2 bridges destroyed. Field observation shows that the soil whale's body graded size with the particle size range from 0.01 millimeter to meters, unconsolidated and non-uniform pore structure are essential the source material for debris flow. So it is widely found in the gully and slope in the mountain areas southwest of China. Large particles usually form a framework of the structure while the small ones fill in the pores. Field observation also indicate that during the rainfall infiltration process, there may exist the phenomenon that fine particles are carried away by the seepage force, which is known as the internal erosion. So in order to study the snow failure mechanism contents wide-grade loose soil, we conducted detailed study based on from test. The figure here illustrates the design of the artificial rainfall from test system. It contains a from and artificial rainfall equipment and monitoring device. Artificial rainfall equipment consists of the rainfall sprinkler head, the pump, the water distribution tank. Valves are used to control the pressure of the area drainage hole and produce different rainfall intensities. During the test, we used monitoring sensors to measure the volumetric water content at 6 different locations in the slope. At the end of the test, we also conducted the grading analysis of the soil from 3 different locations. One of the most important things that we would like to identify is the direction of the fine particle migration. Here we use the particle grading analysis of different locations in the slope. You can see the content of the fine particles after the test is more than the initial stage. We consider this is an indication of the fine particle migration direction. And the fine particle will accumulate at the slope tongue. In order to further prove this, we have also conducted the particle grading analysis of the samples taken from 3 different slope locations after the experiment. You can see there's a general trend that the fine particles content is higher at the slope tongue. We use the front side and side radio cameras to record the whole failure process. After the data interpretation, we mainly divide the whole failure process into 3 stages. In stage 1, the increase in the water content in pores and fluid flow caused the fine particles start to migrate. The enlarged pore provide better space for the fine particle, even for the coarse particle to migrate. And the accumulation effect of the fine particle migration changes the structure of the skeleton grains, which reduce the skeleton stability and induce a small collapse locally. In stage 2, some soil pores are blocked by migrated fine particles. The fine particles accumulated at certain layer of the foam and form a relatively impermeable layer, which will cause the pool pressure to increase and the soil strength decrease. This is also verified by the pool pressure measurement data. In stage 3, the equilibrium state will be broken. Thereafter, the same effect may induce another collapse, and similar process may happen continuously. So this kind of domino effect would make more fine particles to flow out and finally lead to the whole slope failure. From the experimental study, we know that the whole picture of the failure including in 2 stages. The first is internal erosion, and second is the combination of the internal erosion and surface runoff. So the current research focuses on the investigation of the first stage of mechanism. So in these soils, the micropore structures governs the spatial variation of the seepage channels and therefore influence the fine grain migration during the rainfall infiltration process. Due to the broadly graded size, undetermined pore structures, the mechanism of fine particle migration during the rainfall infiltration process remains unclear. Before we go to the next step, I would like to review a little bit on the previous research of the numerical analysis on the internal erosion phenomena of the non-plastic soil from the perspective of continuous, discrete, and even both. There are 2 fundamental frames for describing the physical governing equations, the Lagrangian description and Eulerin description. The Lagrangian grade is fixed to or attached on the material in the entire computational process, and it moves with the material. One typical example is the finite element method. The Eulerin grade is fixed on the space in which the simulation object is located and moves across the fixed mesh cells in the grid. One typical example is the finite difference method. Here is the comparison between the FEM and FDM. For finite element method, it is well performed in solid deformation problems, while large deformations such as fluid flow cannot be well simulated. For finite difference method, construction of complex geometry will never be an easy task. It cannot solve the problem that need monitoring the material properties in fixed volume. So what we need actually is a method not based on the grid, allowing the internal structure to be more adaptive and robust. So here comes the mesh-free method's smooth particle hydrodynamics. There are 6 key ideas in the SPH method. The first one is mesh-free, and the second one is integral function representation by the kernel approximation. And then is the compact support, adaptive, when the Lagrange means that the particle approximation is performed related to the field functions. Dynamic state that the using an explicit integration algorithm to obtain the time history of all the variables. So the formulation of the SPH is often divided into two key steps. The step one is the kernel approximation. The function is approximation by summing up the value of the nearest neighbor particles, converting the discrete particle to continue by integration. Step two is the particle approximation, makes the SPH method simple without using the background mesh for numerical integration. As for the general dynamic flow, SPH is applied to Navier-Stokes equations or Euler equations. So the application of SPH, which has a wide range, from computational fluid dynamics to computational solid mechanics, from micro scale to macro scale, and from discrete system to the continuous systems. Here is another measuring method, which is called the material point method. It is an extension of the finite element method, and the continuum is represented by a Lagrange point, which is called the material point. The deformation of the continuum are modeled by tracking the particles that move through an unirine fixed mesh. And the computational mesh is reset to its initial configuration at every iteration. At the beginning of the time step, information is transformed from particles to the computational mesh to initialize the discrete equation of the motion. And the mesh is used to determine the incremental solution of the field equation in Lagrangian fashion. At the end of the time step, the solution is mapped from the computational mesh back to the particle to update their information. Here is the summary by comparison the SPH and NPM. Both are mesh-free methods. NPM also have some grid, but it only used to calculate gradient terms. They can both be used to handle the irregular geometry and notch deformation, but limitation also lies in the balance between the computational efficiency and accuracy. Another limitation from the SPH and NPM is that it cannot deal with soil with wide particle size distribution. So this can be solved by discrete element method. The DEM is independent of displaced independent of one another and interact only at contact between the particles and the boundary. The particle motion of each discrete element is calculated from the force acting by the Newton's law of motion, and the displacement and rotations of the discrete element were computed as the calculation progressed. A new contact and completed detachment between the discrete element were recognized automatically. As we know that the dry DEM is not able to simulate the fluid flow in pore channel, and the interaction between the fluid and solid is the most critical physical process of soil failure. So numerical simulation method that's considering the fluid and solid coupling are more in line with the fundamental mechanism of the soil failure. So I will first talk about the solid and fluid coupling in the NPM method. Here, the balance laws are applied for soil and water points separately. Each material point has their individual motion, which is annulled in time due to the Lagrangian description. The solid skeleton and the water material point that are located at current configuration might have located at different locations in the reference configuration. In this formulation, the momental balance equation are solved to obtain the accelerations of the solid skeleton and the fluid phase. The momental exchange term is considered in the fluid momental balance equation. A lot of researchers have been working on the development of the solid fluid coupling techniques using the discrete element method. An overview of this approach is divided into three categories. The first one is a DEM coupled with computational fluid dynamics. The governing equations of the fluid calculation system are the continuity and Navier-Stokes equations. Fluid-solid interaction force is applied to the solid particle by drag force. One difficulty with this kind of approach is that the solution of the mass balance and three momental equations are computationally demanding. The second division is the DEM coupled with the lattice Boltzmann method. Here, the fluid is presented as the packs of the mass that move on a regular lattice, gradations and redistribution of fluid packets that occur at the lattice node according to the conservation of the momentum. The coupling of LBM and DM is accomplished through a moving solid boundary condition, and the fluid-induced force was calculated by summing up the momentum term transfer that occurs over all the nodes converted by the solid element. The total computational cost could be substantial since the fine lattice is necessary and small time steps are required. The last one is the DM coupled with solid deformation and pore pressure. The pore pressure change was calculated from pore volume change, and pore pressure force on the particle is applied by integration method of pore pressure difference on the adjacent center of the pores. However, the computational efficiency of such method still need to be improved. So here's the comparison of the different coupling methods. We can see that each method has its advantage and limitations. NPM still cannot, two-phase coupling cannot deal with the particle size distribution, and DM coupling with the CFD is not able to calculate the hydraulic fraction. For the DM-LBM coupling, large number of solid particles induced extremely fine lattice mesh, and DM-SDP coupling need to combine with the CFD to simulate fine particle migration. So I will first start by talking about the categories of solid fluid coupling analysis before I introduce the development of the coupling schedule. The first one is the hydrostatic pressure of the fluid in the buoyance. When the particle is simply submerged in the steady fluid under the gravity, the only force that the fluid adds on the particle is the buoyant force. The second one is the no solid concentration flow. If the particle moves independently of each other and they only occupy a small fraction of the fluid volume, viscous force is applied to each particle, and the presence of the solid has no effect on the fluid flow. In the case of the solid concentration, high solid concentration, not only the fluid flow will contribute the drag force on the particles, but the particles will also have the effect on the fluid flow. Here, the permeability can be calculated from the DEM, and it will be used in the fluid flow calculation using the continuum approach. This coupled approach is able to capture the mechanisms such as internal erosion. The last one is solid fluid deformation coupling. So when soil or rock is fully saturated with the fluid by impermeable layers, the compression on the outer boundary will cause the void space to decrease, resulting in the increase in the excess pore pressure. The increase of excess pore pressure will cause the displacement of the solid particles, and the movement of the solid particles will change the void space that is occupied by the fluid. An example is the consolidation problem in soil and large displacements caused by the liquefaction in the sand during the earthquakes. So we first start with the pore pressure generation process for the SDP coupling procedure. So when the sample is subject to the isotropic compression, the solid particles are considered to be incompressible. However, the intersection of the particles at contact is allowed in order to model the reduction of the volume of the void. The pore space volume change can also be calculated. When the material is fully saturated, the volume reduction in pore space will cause excess pore pressure to build up. Therefore, we introduce the water element in the DM simulation. Compared with the specific solid element, the water element is assumed to have the same center of position and radius. The water particle deform together with the solid element, which means that the same deformation at each contact is calculated compared with the solid particle. The pore pressure generated from the deformation of solid particle is now considered as an outer boundary pressure on the same that only consider water particle. The water element slip is then calculated related to the change of the pore space and the compressibility of the water. In relating the pore water pressure in a water element to contact the force acting on the water element, the pore pressure can be related to the average mean stress due to the water particle contact forces. Since water particle has zero shear stiffness, the only unknown is the normal stiffness of water particle. The pore pressure in an undrained sample is averaged along three principal directions. The water particle stiffness is then calculated by using the average method. During the water diffusion process, The effective stress is carried by the solid particle, and the pore pressure is carried by the water particle. During the water diffusion process, the total stress on the outer boundary wall is maintained the same, and the solid stiffness remained unchanged. However, the volume of the total sample decreased due to the drainage of some pore pressure. The DEM simulation here reduced the water particle stiffness in a certain amount to maintain an expected volume reduction. We consider two particle packing configurations in pore pressure dissipation simulation. First, the loose particle packing configuration with uniform particle size is considered for 1D consolidation. And the force between the particles is only transmitted in the vertical direction along the z-axis. Therefore, during the drain dissipation process, there is no force acting on the side wall of the x and y direction. During the consolidation, the pore pressure can be linearly related to the particle contact force calculated from water particle stiffness. For irregular packing case, the force between the particle is not only transmitted in the vertical direction, but also transmitted in the horizontal direction. Therefore, the linear relationship between the single force induced by water particle on a contact and the pore pressure of the whole sample no longer exists. In this case, the water particle stiffness can be determined using the iterative scheme. In the DEM calculation, because each particle will have its own pore pressure reduction factor, the pore pressure calculation is based on the individual particles. For numerical verification of the undrained isotropic compression case, the DEM particles are generated in a cube box. During the undrained test, a continuous outer boundary total stress increment is applied in steps. The isotropic stress of 1 ampere is first applied on the sample with the solid particle only case. The calculated water particle stiffness is then applied back to the original sample. Then both soil and water particles are activated and experience an outer boundary total stress increment of 1 ampere. The water particle stiffness for the next loading increment is adjusted based on the pore pressure difference. For the numerical verification of one drain triaxial compression case, the model generation and test procedure follow the same procedure as the isotropic compression case. The result of the isotropic and triaxial compression test show good agreement between the analytic and numerical. The analytic solution for the Terzachi's 1D consolidation test can be calculated by considering a half drain layer. The excess pore pressure at any distance from the drain layer is calculated from the drainage path and time factor. The final 1D consolidation settlement of the whole soil layer is calculated based on the change in the effective stress and the coefficient of the volume compressibility from the DM dry case. During the drain condition, the water particle stiffness is reduced from the maximum value to 0 corresponding to the pore pressure dissipation. The difference in pore pressure along each layer in the analytic solution will result in different stiffness reduction in the water particles in the DEM. The consolidation settlement of the whole soil layer is calculated by the wall displacement. The comparison of the excess pore pressure drop in each layer between the DEM and analytic solution shown here. The last figure shows the comparison of the consolidation settlement of the whole soil sample against the time increment between the analytic and DEM solution. Both show good agreement. Let's talk about another solid fluid coupling development during the flow-driven condition. The continuity equation for the fluid flow is expressed as the difference between the entering and exiting mass being equal to the accumulated mass. By combining the Darcy's equation and compressibility of the fluid pressure can be solved at grade point of superimposed mesh element. The fluid compressibility here is assumed to be constant. The fluid force calculation method adopted here assume a continuum where the size of the grid block for the flow calculation is relatively large compared to the average particle diameter. A shape function is used to interpolate pore pressure at any point inside the grid block from the calculated nodal pressure in the cylindrical coordinate system. The fluid force applied on each particle in the fluid cell is calculated by integration method of the pressure on any point of the pore surface and area of the pore. To update the permeability we determine the number of the particles in the measurement sphere at the beginning and end of each time step to track the particle movement. If the number of particles at the beginning is found to be equal or smaller than the number of the particle at the end of the time step, so no standing is assumed from that volume. In this case, the permeability is updated based on the volumetric string using the modified version of the Korseny-Kammer equation. If the number of the particle at the beginning is found to be larger than the number of particles at the end of time step, the permeability is updated based on measured porosity. If the porosity measured in this block is smaller than 0.85, the permeability is interpolated between the original permeability and an upper bound value. If the porosity exists 8.5, the gray block is assumed to the fully sanded. In this case, the permeability is assigned as 100 Darcy. The model here was verified against the result of the analytic solution. We used the castigate sandstone properties in the analytic and numerical models. The figure here compared between the numerical and analytic of both radial and tangential total stress behave along the radial direction. The width of the plastic zone can be considered as the extension from the face of the borehole to the location of the maximum tangential stress. From the lower figure, we can see that the plastic zone has already been developed around the hole, even when there is no fluid flow. However, with the introduction of the fluid flow, the plastic zone further expands in both the numerical and analytic model. We studied the effect of boundary effective stress and pressure on sandstone degradation and sanding. Here, two cases were considered, one with the horizontal effective stress equal to 60 MPa, another with the maximum and minimum horizontal stress equal to 60 and 30 MPa. In both cases, the outer boundary pore pressure was kept a constant at 10 MPa. A map of the broken bond is shown here. The red indicates the bond failure intention and blue for the shear. A relatively uniform breakout is observed for the case with the uniform boundary stress, and the V-shaped breakout is observed for the uneven boundary stresses. Some sand particles are observed to be produced from the breakout zone after the application of the fluid flow. The right figure shows the effect of the minor principal stress on the produced sand. As expected, larger amount of sand is produced for the case with uneven boundary stresses. We also simulated a synthetic sanding test on the hollow block sample. In the simulations, the outer boundary effective stress was increased gradually. Within each boundary effective stress increment, the fluid pressure has a step rate increase. The left figure indicates the onset of sanding at the outer boundary effective stress of 30 MPa, and massive sanding occurs when the outer boundary effective stress and pressure reached 58 and 20 MPa. To further examine the whole fluid flow, we repeat the same analysis, but change the final modeling test setup. The last loading step in the right figure shows that the boundary effective is equal to the 65 MPa with lower boundary pressure of 1 MPa. In this case, we observe much less sanding. After the numerical development, I would like to start from the basic pore structure characteristics of the WG areas. So to study the micropore structure of a typical source material from debris flow, we collected the soil samples along the Subao River basin near the Leigu town in Sichuan province, China. The sampling location were 130 kilometers from the epicenter of the 2008 Wenchuan earthquake and experienced seismic intensity of 11. The study area is fully covered by the loose landslide material, and that has high potential for subsequent debris flow under the heavy rainfall. Table here described the geomorphology based on the different Earth surface process and basic soil properties from the particle size distribution. We use the serial topographic method, which is known as the ST method, based on the SEM analysis to characterize the pore structure in the study. So the sample are well prepared with epoxy impregnation to protect the micropore structure before go to the SEM scanning. After each scan, we will train 50 micrometer of soil along the depth direction using a grinder. We use the unit number to describe the pore conductivity. The calculation of the unit number is shown here. For 1D case, the unit number is defined as the number of disconnected pore along a straight line. In 2D case, the unit number is the difference between the number of discontinued pore in ZX and the total number of separated soil particles. However, in 3D case, the unit number is calculated by adding the number of completely enclosed cavities in the ZX. To obtain the pore size distribution, we use a numerical technique which is similar used in the particle size distribution. We reconstruct the structure element with the unit element of 12 times 12 micrometers. We totally construct 6 structure elements to act as a safe mesh. Figure below shows the pore distribution under different pore scales. The number of pore decrease as the gray pore size increase. From the previously literature, pore size more than 12 micrometers were classified as the micropores, which means that fluid flow is unlikely. So the number of the pore and their size influence the mechanical response of the soil, especially when there is an overwhelming high number of large pores, which is larger than 1,000 micrometers. For each sample, the number of pores decreased rapidly as the pore radius increased. The large pores were found in the samples ASB and CHS, but the observation showed that the all samples were dominated by the pore with the diameter smaller than 150 micrometers. The probability distribution can be used to highlight the different pore size as well as generated the random 3D pore medium. Here we can see that the pore radius in the soil samples generally obey a Reemann distribution. During the sampling, the y direction was denoted as the downslope along the slope surface. The pore frequency was then obtained by dividing the index by the total number of pixels occupied by the pore in each soil sample. To further illustrate the pore distribution in 2D space, we apply a statistical approach based on the superposition in the x and y directions. This figure shows that the pore frequency distribution in the x direction, compared with the 3 other samples, the distribution frequency of sample ASB reflect the relatively large pore concentration. When we find that x is larger than 3 and smaller than 5. We also find that the pore distribution frequency increased sharply in the y direction in some variation when y is larger than 8 millimeters. Here we develop a new dimensionless number, NC, to present the pore complexity. So NC actually is ranged from 0 to 1. A high NC indicates that the shape of the pore is close to a circle, and a low NC indicates that the pore has high complexity. It was observed that the pore complexity of all samples remained above 0.75, which suggests that higher circularity and low aspect ratio of each pores. The overall conductivity of the 4 samples in 3D is reflected by the unit number. And the unit number indicates that the high pore conductivity, and should be noted that the pore conductivity only increases with a decrease in the 3D global unit number when the stem radius are found among pores. So although the 3D global unit number reflects the overall pore conductivity, low conductivity does not necessarily mean that the low permeability. Pore with complex branches may not provide sufficient seepage channels due to the branches blockage. We compare the pore size distribution of the white-green loose soil samples with the NERS data. Those samples are prepared with the same method. We can see that the pore size distribution of the WGLS is significantly different from the NERS. The NERS pore size distribution shows a normal distribution with a single peak at 13 micrometer. In contrast, the WGS pore size distribution shows a double peak at 12 and 72 micrometer. The reason for the high percentage of the micropore in the WGLS is because the fine particles are locally concentrated. The diameter of the pore in the NERS shows a large volume percentage, which is significantly smaller than the mesos pores studied in the WGLS. Compared with the bidomal pore size distribution of the silty soil and sand from previous literature, the WGLS also corresponded to a second peak with a larger diameter. This is attributed to the widely graded characteristic of particle size distribution in a coarse soil skeleton that forms more macropores. However, the ST method we used here is not able to capture the peak pore with a diameter smaller than 2 micrometers, so we cannot get any information from them. We identified that the size of the migrated fine particle from the soap tongue after rainfall was smaller than 2 millimeters from test. We know this size only serves as the upper boundary. So in order to obtain the exact D50 of the migrated fine particles, we conducted 1D colon CPT test, and the experimental aperture is shown here. We found that the D50 of the migrated fine particle was an average from the 4 samples as 0.015 millimeter. For the jamming analysis, we simplified the model and assumed the soil was in a fully saturated state for calculating the jamming probability of each sample. The fluid was assumed to flow continuously along the channel by pores. The fine particles were transported by the effect of fluid flow. The discharge velocity of fine particles passing through a specific pore is significantly related to particle and pore size. The flow rate of the grain through a hole was first assessed using the Beverly's law in 1961. But sooner after that, the literature found that the Beverly's law is not applicable when the small hole exists. So flow rate calculation is then adjusted from the experimental observations from Jenda 2012. The probability of the jamming for different pore and particle size is shown here. The results shows that the jamming probability decreased sharply with an increase of the pore size and decrease in the particle size. The jamming probability of the 4 study samples was then calculated by the regular square mesh at each size. The chosen mesh size was 1.6 times larger than the maximum pore diameter, and the calculation is based on the average migrated fine particle size of 0.015 millimeter from the CPT test. The result shows that jamming will be most prevalent along the slope direction, and this is attributed to the relatively smaller distribution of pores in terms of the pore size and number near the bottom of the slope. So the average jamming probability downslope for the 4 samples actually is 2 times greater than the upper slope. The influence of the average pore complexity and the 3D unit number on the average jamming probability of each sample is shown here. Also, we can find a linear relationship between the average jamming probability and 3D unit number, but the influence from the pore complexity were mainly quantified independently. So a more systematic investigation with more samples is required. So from the previous slide, we analyzed the fine particle migration and jamming probability based on the analytic method. And the method has several assumptions and do not consider the effect of fluid flow. So to characterize the effect of pore size distribution on the fine particle migration process in each different samples, we replace each pore diameter from pore size distribution and its mean value. The fine particle diameter together with the pore size will then expand 20 times to improve the calculation efficiency, but we maintain the same Reynolds number to minimize the scale effect. Here we only show 1 layer of the pore structure, and for the simplification, we construct 1D pore structure by the DM grid element and distribute according to the pore size distribution in this study. So the LBM was used to solve the fluid motion process in the fluid structure interaction, and DEM is used to simulate the fine particle migration under the effect of fluid flow. The result of the 3 different samples are showing at 2 distinct times, 0.08 and 0.26. It is observed that the fluid initially causes downstream migration of fine particles. Then there's an interaction of particles and pores, resulting in the jamming effect and subsequent arching formation of fine particles that significantly affect the fluid field. The blocking ratio at the beginning is around 0.4, and this value becomes really, really low at the end. We can see that the right sample TEGZ found to have the highest jamming probability, while the sample A has the lowest jamming probability. This also follows the pore size distribution, which means this is dominated by the second peak, while the sample TGZ is dominated by the first peak. The same observation is also found from the analytic jamming analysis using the modified version of MODULUS law. Since the ST method is not able to capture the peak pores with small diameters, we then perform a series of one-dimensional soil seepage tests by controlling the coarse to fine particle size ratio. And then we use the CT scan method to obtain the particle distribution and 3D pore structures. We divide the CT result into two groups based on the coarse particle size difference. The left shows that the fine particle migration starts from the top to the bottom. However, the right side shows that fine particle migration starts from the bottom to the top. This is mainly due to the relatively small size of the pore channel formed by the relatively small size of the coarse particles, while many fine particles present in the channel further reduce the particle transport space, thus erode the bottom particles for the upper fine particle transport to provide the sufficient transport channel. And the other particles are then transported. So it is really interesting if we can do this kind of in the numerical simulation. For the numerical simulation, the fluid equation in saturated porous media is applied to solve the fluid action on particles, which follows Darcy's fluid and mass conservation. And the drag force related to the velocity of the particle was assumed at the center of the particle and calculated as follows. And the fluid calculation time step was determined using the von Neumann stability method, and the flowchart for the implementation of the coupling program is shown here. Here we can see that under the action of the fluid of the fine particles will move along the pore channel in the seepage direction. At the end of the test, the coarse particles locally displaced and rotated slightly, and part of the fine particles were eroded away and even flow out, which resulted in the formation of the large holes in the soil samples. By the comparison of the CT and the numerical results, we observed that the fine particles located at the upper were eroded, especially in the middle part, because the relatively less energy of the fluid was consumed. The fine particles in the middle of the sample were eroded less due to the particle supplies from the upper. But there are relatively less particles in the middle of the numerical result due to the large space of migration. The relatively numerous fine particles located at the bottom were eroded, especially in simulation, due to the lack of supply of the particles from the upper part. The result of CT and numerical calculations revealed that there existed perforation erosion in the inflow and the outflow region of the soil sample. Meanwhile, we also observed the clogging area with the slow fine particle velocity or even zero velocity. Therefore, we choose two zones to monitor the fine particle migration. We use the average kinetic energy as an indicator of the monitored zone. So when the numerical simulation is calculated to 2.5 seconds, we see that 37 and 32% of the fine particle had been eroded in above two regions. And the form of the fine particle erosion inside the soil in the direction of seepage induced the loss balance of loss and supply and grid erosion. The average kinetic energy of the fine particle tend to increase along the seepage path. On one hand, the forming of long-term clogging or jamming to the flow channels is reflected by the decreasing of the average kinetic energy and quantity of the fine particle with time. But on the other hand, the temporal jamming to the flow channels is also reflected by the rate of increase of the number of fine particles in the measurement region, rather than the rate of the increase of average kinetic energy. Okay. here I just need to get a little bit conclusion and recommendation for the current study. A quantitative analysis of the relationship between the micropore structure and the mechanical behavior need to be combined traditional geotechnical experiment and pore structure analysis from a microscopic point of view. And further laboratory triaxial tests of fine particle migration and undrained rain shear tests need to be carried out to understand the influence of fine particle migration on the pore pressure and soil stress. The use of the discontinuous mechanisms in the simulation of the sanding poses a serious deficiency, as the application of the particle method to the large-scale problem is currently difficult. So the restriction of the DM in the simulation of the large-scale problem can be reduced by bending the continuum and DM models. When deal with the wide-grade soil, the current fluid mesh dependent drag force calculation does not capture the particle of the various sizes. So it is recommended to use the semi-resolved DM fluid flow model to precise calculate in the future. In the future research, it is also suggested to consider the influence of the pore structure, scan aperture distribution, and reconstruct the pore structure in the 3D way to provide a theoretical basis for the numeric simulation. So here's the publication that related to the current study, and here is the reference related to the current presentation. And thank you so much.
Thank you, Professor Kui. That was an excellent presentation based on, I mean, it's amazing the work that you have done based on the numerical modeling on soils. There are a couple of questions. So let's start with the first question. Is there any relationship between material pore distribution and conductivity resistivity?
Sorry, can you repeat the question? So is this?
So there's one of our attendees that he's asking, is there any relationship between material pore distribution and conductivity or resistivity?
Yeah. There's some kind of relationship between the material pore distribution and hydraulic conductivity. So actually, this kind of relationship has been studied in the past decade from many researchers, not only from soil, but also from the rock and the material. So this kind of relationship, actually, we need to use some kind of the index to quantify the pore structures. For example, if we only focus on quantify the shape of the coarse particles, so we have the two index. One is for the shape, one is for the roughness, right? But if we want to use some kind of index to quantify the pore structure, so it will be more complex, because for the pore structure, we have the conductivity, we have the tortuosity, right? So this kind of relationship, we cannot use the traditional Cosine-Common equation to do this kind of simulation, because the traditional Cosine-Common equation is calculated only based on the porosity measurement. But we know that when you have some kind of small porosity, but you have the correction between the pores, which means you will have some kind of hydraulic conductivity. So now we dig in some literatures. We want to quantify this kind of relationship, and I think this is the next step. That's what we are going to study.
So the next question is, how can pore distribution of material influence its rheological behavior?
Okay, the pore distribution of the material and for influence the rheological behavior, and sorry, okay.
No.
Okay. So you mean the rheological behavior? You mean that the behavior with the for example the viscosity, something like that.
Yeah, the viscosity, right? Exactly.
Oh yeah. Of course, this will influence that a lot. But when you study this kind of thing, you need to we usually do this in the microscopic point of view. wheel, and after we understand that, we just gradually go to the macroscopic. So from the microscopic, we know that there's some kind of pore channel inside, and when we have the fluid flow in this kind of pore channel, it will be influenced because you know that the fluid flow in an enclosed channel, the velocity distribution will not be equal when you have a channel surface or at the center of the channel, right? So this kind of to deal with this kind of problem, so we just now we only simplified everything that's we do not consider too much the side effect on the channel, and we use the computational fluid dynamics, we calculate that. But of course, when you transport the fine particles in that, we will have some kind of the blocking effect, and with the increase of the transport in the fine particles, the flow behavior will be differently when we compare with the clear water. So this, I think, this will also be considered in the future simulation, numerical simulation, and also the experimental approach.
Next question is, what impact do you expect non-spherical fine particles to have on particle movement and pore blockage?
Oh yeah, the particle shape actually has a lot of impact on the pore blockage. So if we only consider, we do not consider the cohesion of the particle, we only consider the particle shape. So this will have, for example, if we have the ellipse particle shape and compare with the spherical particle shape, the total blockage the blockage effect will be totally different. And currently, we only use the spherical particle to do some kind of simplification analysis on this kind of problem. If we want to consider this, and in the discrete element analysis, we can use the clump to form different shape of the particles and to do this kind of simulation and see how this kind of particle shape will influence the pore blockage and the arching effect.
Next question is there a difference in behavior between fine particles formed of clays rather than silicates? Is this a function of fine particle size or material composition?
Okay, so let me clarify this a little bit. The study on the interoerosion, actually we have a lot of influencing factors. So in this study, we mainly focus on the size exclusion. The size exclusion means that the fine particle size, the size of the fine particles to the pore size. Okay, but at the same time, from the macroscopic point of view, we also have the fine content and particle size distribution. So for the shape of the particle size distribution, we will have the CU, CC, and a lot of indicators to describe this. And all of this will influence the migration of the fine particles. Together that we also have the hydraulic gradient, stress field, and the particle adhesion. So if we want to do this, we have to solve this one by one. We cannot solve all the problem at the same time.
So it's as always in many studies. So the last question is, in numerical models, coarse particles don't move. Would you expect coarse grain movement, soil skeleton collapse to alter the relative fine particle migration behavior between different zones in the soil?
Yes, I think this is an excellent question. So in our current numerical simulation, and we just fix the coarse particles, and we want to simulate how the behavior of fine particles with the flow channels. But the coarse particle actually can move because the previous researchers have done some the experimental work using the triaxial test, and they for example, the Professor Li Zhang from the Hong Kong University of Science and Technology, and his group did some kind of the triaxial test after the seepage and the fine particle migration. So in this kind of the test, the coarse particle from their experimental and both numerical simulation, the coarse particle actually can move, and it will contribute a lot to the macro property of the soil.
Okay, yeah, true. So I think there were a lot of questions for Professor Cui, as his analysis were a lot deeper. So I would like to invite once again also Professor Abam. I would like to both thank you for accepting YEG's proposal in order to present your work in relation with the session called e-YEG. So e-YEG is a monthly session that will keep present you different kind of topics related with engineering, geology, and the environment. In order to conclude this session, I would like to thank you once again, Professor Cui and Professor Abam, for present your work. I hope if someone has more questions, I'm sure that Professor Cui and Professor Abam are available to contact them via their emails. Thank you very much, Professor Cui. Thank you very much, Professor Abam, and thank all the attendees for being today here in this session.
Okay. Professor Stratis, so I have additional questions for you. So I just wonder if the whole session is now recorded and will be shared on the YouTube, right?
Yes, definitely. I mean, the current session and each session is
because one of the audience is asked the same question if they can see the playback of the videos of this presentation. Yeah.
Definitely. I mean, as I already posted in the chat session, it's e-YEG session is being recorded in a live stream via our YEG's official page in YouTube, but you can find it also in an offline edition after the meeting has finished. Also the last one, but also the previous sessions. So please feel free to share it. And if you have any queries about that, the presenters will definitely help you with that.
Okay, thank you so much.
Thank you very much, all of you.